All right, I think we're sort of live. I think it's moving. We're having to do a little bit of a slower stream today, so it might buffer a little. We'll see. What we're talking about is, again, a continuation of beams in bending. We last time talked about how to draw shear and bending diagrams, and we did an example. I think we just did one example. Maybe we did half of finishing one and then one from start to finish. So we'll do another one of those because that is still going to be kind of at the core of how we're going to get to some of the other things we're going to do. Our real goal is we want to deal with these beams that are flexing or bending, and we want to calculate a bending stress in them. Or maybe we want to calculate how much they deflect, how much they bend downwards or up. Sometimes they'll bend upwards depending on how you've loaded them. And so in order to do those two things, we need to know something about the bending moment and sometimes about the shear force inside the beam. And so that's what the shear and bending diagram does for us. It shows us those shear forces and bending moments inside the beam. And we could also, chop the beam up at a given spot and find the same thing for that one location. So we're going to do some more of that, but we're going to add on to it this idea of moments of inertia for the beam's cross-section. So we talked a few weeks ago about centroids and how at the centroid of a beam's cross-section, we didn't have any flexural stress. There was zero flexural stress. And we drew a picture. Let's look at what we drew, or something like what we drew. We drew a picture kind of like this, where we took I wonder if I have a shape that's already a beam shape. No. Okay, that's fine. Hey, there's the snap to grid. We could turn that off. So we did a beam kind of like this. Very exaggerated amount of deflection. And we said that if this beam started out horizontal, this is a side view of a beam. So this is side view. If we started out horizontal, flat, not bent, we put some kind of loads on it and it ended up bending, then somewhere in here, it's the original length, because we can, figure that out because on the bottom here, it's had to stretch. So there's tension on the bottom. And at the top of the beam in this loading configuration, or we wouldn't even show the loads, but the loads that create this kind of deflection, the beam has gotten shorter. It's in compression. And we know that if on one side of this dotted line that I've drawn, that's the original length, on one side it's shorter, and the other side is longer, that means somewhere in the middle-ish of the beam, there is no change in length. It's not tension or compression. It's not getting longer or shorter. And so that axis we called the neutral axis. And we said that if we knew what the cross-section of this beam looks like, here's the side view of it, so that's not really the cross-section that we're thinking of. If we knew that this beam was an I-beam or a T-beam or just a rectangle or whatever it is, then we could figure out that the neutral axis is going to occur, or exist, whatever you want to call it, occur at the centroid of the beam's cross-section. Okay, and so we did that. We were calculating centroids of 2D shapes. We did that with kind of this bookkeeping method where we created a chart of individual areas. Then one area might be a rectangle, another might be a triangle, and we were combining all these primitive shapes into a cross-section that represented the shape of the beam's cross-section. And then we could figure out the centroid's location based on that chart that we were making. So that's something we still need to be able to do. We still need to be able to find the location of a centroid. The moment of inertia is related to this idea of a centroid, and it is going to be sort of describing the beam's resistance to bending. We actually have used it already. We had our equation a long time ago, or several days ago anyway. Sigma, meaning sigma bending stress, flexural stress in the beam, equals negative m times y, and then this denominator was the moment of inertia for the cross section of the beam that we were looking at. And you can kind of see it's the denominator of this equation. It's a cross-sectional property, so it does depend on the shape of the geometry of the cross-section. And the larger it is, the less stress I will have in the beam, you know, just looking at the equation. And the smaller it is, I will have a larger stress given the same m and y. M is that internal bending moment. If you don't remember what y is measured from the neutral axis to the point that you're interested in. So usually you're looking at the cross section of a beam, and it's from the neutral axis all the way to the top of the beam, or maybe all the way to the bottom of the beam, whichever distance is further. So we'll do some more of that later. But how we dealt with moment of inertia when we were just using this equation was we went and looked over here. Let's see here, and this is moment of inertia. That's not where we looked. We looked here, and maybe we looked at an S section. So that's a standard flange I-beam. So let's look at those. I don't think we actually looked at that one, so it'll be a good one. So here we have these charts. Now these are kind of generic charts from your book. You would need the actual charts that match up with the beam that you're using, but these will do for now. And you got the beam designation over here, so you know what kind of beam, you know roughly what size it is. And then over here, you've got axis XX, there's an I under that, so right there. And axis YY, there's an I under that. So we've got two columns of moment of inertia. And so you can just look this number up if you know the beam's designation, you know its name over here. There are two of them because remember there are two axes up here, XX and YY, and that matches up with XX and YY over here. And the beam could be loaded perpendicular to either of these axes. So normally it's loaded perpendicular to the XX axis, meaning that there are loads pointing downward on the top of this beam. They could be pointing upwards, but they're pointing perpendicular to X, so it's either up or down. But they could have loads on what I would call the side of the beam here. So they could have loads that are perpendicular to YY, and in that case you get a different value for the moment of inertia. In fact, they're very different values. So remember, it's in the denominator of our stress equation. It's also going to be in the denominator of deflection equations when we calculate the amount of bending that occurs, like the number of inches of bending or millimeters or whatever. It's going to be in the denominator of those equations also. And notice when you're talking about loads that are perpendicular to XX, which is the normal orientation, you get really large values of moment of inertia compared to those for the same beam but loaded on its side. And so a lot of beams, not every beam will be that way. Some beams are symmetric, they would be the same either way. But I-beams and T-beams and C-beams are going to have one direction that's much stronger than the other as far as bending and flexural stress go. So we just looked this number up. But we do have charts like this that have shapes. So we got rectangle, triangle, circle, half circle, quarter circle, and sector of a circle, and a bunch of equations over here that we can do the same type of thing as when we were doing the centroids, and we had a chart that looked like this for centroids, and we could go and figure out, okay, I could kind of cobble together my own cross-sectional area and then I could use a chart like this one to figure out the moment of inertia of anything I can cobble together. So let's do that first. So one thing you can do, just look up the moment of inertia from a chart if it's a standard beam that you know the name of. And so there are several of these charts in your book. There's a couple of them. Actually, I guess they're all in, all the ones that we have access to for the book and you'll need for the course are all in these exam reference 1 and 2. And I've pulled out some of them. So WT, W, S, and C I've pulled out. I think these are only the US units though for all of these. I don't think these are the metric units. Yeah, these are only the US units. You have a matching chart with similar beams but metric units for each one of these beam types. All right. So we could do that. We could just go look up a number, but let's go and see what if we don't have one we can look up. So let's do the simplest, well, the next to simplest one that we could think of. The simplest one would just be some kind of rectangle or circle, you know, one of the ones that's just in the chart the way it is. But let's say we've got something that's not in the chart. Let's get some room here. There we go. Let's make up a T. So there are T beams already standardized. We had a chart for the WT, so the wide flange T beams, but let's say that we want to create our own for some reason. And we're going to make it out of 2 rectangles. Let's make one for the flange. And let's make, whoa, that's not what I wanted to do. I went kind of crazy there. Let's make one for the stem here. On the I-beam, this part is called the web. It sits between 2 flanges. On a T-beam, this part that's kind of highlighted is called the stem. It looks like our stream is a little bit slow right now. I'm going to let it rest and catch up. For a second. I think it's kind of catching up now. All right. If it's in the chat, see, I don't know what y'all see. I kind of get a preview of what you're seeing, but I don't know exactly. So if it's really bad, let me know and I'll give it several minutes to catch up. But it looks like it's relatively okay. It's behind, but it's not that far behind. All right. I don't have Discord running right now, by the way, just to try and save some bandwidth. So I won't get those messages. I'm just going to put some dimensions on here for our homemade T-beam. Okay, so in order to, oh, okay, well that's a problem, huh? Let's go to the OneNote screen. There you go. All I did is I drew this T shape. So this is our homemade T-beam. I've got an 8" by 1" flange on top. Oh, I was talking about the flange, stem, and web. So just so I can go back over that. This is the flange, whether it's an I-beam or a T-beam. These top and bottom pieces are called flanges. In a T-beam, this is called the stem. And in a I-beam, one that has flanges on top and bottom, this is called the web, this yellow piece. So, yeah, there's some chats that it does come back eventually. So we'll see. So this is, doesn't match a WT beam that we could go find. We could find one probably close to it, possibly. But this one is sort of our own version. So the first thing you have to do before you can do the moment of inertia, if you have a cobbled together shape that you're dealing with. So it's not one of the standard ones, or it's not just a rectangle or something like that. Is you actually have to go find the centroid. So the very first thing we have to do with our shape is we have to find the centroid of it. So I'm going to divide this obviously into two pieces, the flange and the stem. And we're going to go just like we did with the centroids before. Oh, well, let's do part first. Not that it particularly matters, but I like to keep track of it that way. So part 1 is the flange, part 2 is our stem. Then let's calculate the area. These will be in square inches. Part 1 is just 8. Part 2 is, well, I went and put it at 1.5. I wanted different numbers for everything so that it's easier to track them, but that made it harder to multiply. 10.5. So the summation, the total area, 18.5 square inches. Now, we can be smart about where we put the axis for reference, and we'll just put the y-axis right through the middle. And we'll put the x-axis down at the bottom. So doing that means that we know that x sub c is 0 because of where we put the origin. So we don't even have to worry with it. We just want to know y sub c. So how far above the bottom of the stem is the centroid, and therefore the neutral axis. That's what we really want to know, is where's the neutral axis, and the neutral axis is located at the centroid of the cross section of our beam. So let's do y sub c. That'll be in inches for each part. So I usually like to go in and kind of draw in some indicator of where each one is, just so I don't lose track. And in this piece, it's not that hard because there's just two rectangles, but it looks like the part 1, the flange centroid, is 7.5 inches above my reference x-axis, and 3.5 inches for part 2. And then we do a times y. That'll give us units of inches cubed. So we got to do 8 times 7.5, 60. And we have to do 10.5 times 3.5, 36.75. Add those together to get 96.75 inches cubed. Y sub c equals 96.75 inches cubed divided by 18.5 inches squared is, let's see, 5.23. So that tells us that if we go up 1, 2, 3, 4, 5.23, so right in here, y sub c equals 5.23 inches. That is the neutral axis. So we know that the centroid for this whole shape is right there. Okay. So on an exam, usually when we're doing one of these moments of inertia, I just give you the neutral axis, or I tell you a axis that you're going to assume is the neutral axis. Even it may not be the neutral axis. You don't have to be limited to calculating the moment of inertia about the neutral axis. Like, you can calculate it about any point. For purposes of calculating flexural stress or beam deflection, then you do want to calculate the moment of inertia about the neutral axis. But for an exam problem, I could ask for the neutral axis about any point, just to see if you could do the neutral axis part or the moment of inertia part. I said neutral axis, I meant moment of inertia about any axis. All right. So this might be a starting point for an exam problem. For instance, is what I'm trying to say. You wouldn't necessarily have to go do this part. All right. So the moment of inertia. What we're trying to do is, for this beam's neutral axis, what is its moment of inertia about that neutral axis? And we have these charts here. Well, no, not those charts. We have these charts where we can just look up the moment of inertia, but we have these charts, or this chart, this single one, that gives us various shapes. We only need the rectangle for now, so I'm going to zoom in on it. maybe that's a bit much. Zoom out a little bit. That goes okay. So we've got a rectangle. We've got all these, all this stuff on it. So it gives us the area over here. That's just the area. Some of these have difficult to calculate areas potentially, some of these. So the rectangle is not one of those, but it still gives you the area. It gives you two equations for I. So Ix, I with a reference of the x-axis, and Ix prime, so the moment of inertia about the x prime axis. So most of these have two, some of them have three different reference points. So what they're referring to is Ix, there's an x-axis right along here on the diagram, and there's an x prime, so here's x prime, and here is x prime. There's an x prime axis. Unless you know exactly what you're doing, use the Ix. A lot of times you'll want to use the x prime because, particularly like this equation set, the Ix equation is all of this and the x prime is just this. So why not use this one? Same thing for here. You got this really complicated thing, and then you got a really simple one. And this one doesn't even have an x prime. So we'll get to when you can use the x prime in a minute, but we have to know another thing first. So we're going to just use the Ix for now. So the x, the one without the prime on it, is going to reference, and I don't know if this is true for every centroid chart that exists, but for the ones that we use, this is true. Ix represents the neutral axis of this single shape, rectangle in this case, about its own centroid. So that's true for all of these pictures. Ix is the moment of inertia of whatever shape you're looking at about its own centroid or its own neutral axis. So bh cubed over 12, we have to look. B is, and don't automatically put it such that B is the larger or B is the bottom or whatever. B has to be, in this case, it's the one that's parallel to what you've defined as the x-axis. So there might be a reason why you want the x-axis to be vertical. In that case, B would actually be a lot of times called h, the height of the thing. So B, when you're trying to figure out what number to put in for B, look at your picture. I want Ix, so I'm looking at the x-axis as my reference. B is parallel to that. So I need the dimension of the rectangle that's parallel to the x-axis. So it does stand for base and height, but it could be that you've got some reason you've reoriented this thing where the B dimension actually needs to be vertical. So just be careful. Don't get into too many habits of just doing things without knowing why you did them. So let's go back over here. So the moment of inertia for just a generic rectangle is I equals bh cubed over 12, and that was Ix, and our picture that would go with that would look like this, where you've got B, you've got H, and you've got the x-axis. Okay, so those are how we need to orient all of our dimensions here. So what I need to do with this is similar to what I did when I did the centroid, where I've got the same two parts. There's not a real reason to create a different set of parts. So the same two parts, the flange and the stem, and I'm going to calculate their moment of inertia about their own centroid. And then once we get that figured out, we will translate that moment of inertia over to the parts neutral axis. Notice the stream dropped out a little bit, so I'll give it a chance to pick up. All right, I think we're back. Let me just check and see if we have gotten, I don't know. All right. Let's see. So let's do the moment of inertia of the flange about its own centroid. So the flange has, it's rolled off the top, so let's look at its dimensions. It has an 8-inch dimension parallel to the x-axis, so that's what I'm going to put in for B. So this will be the moment of inertia of the flange equals 8 inches. It has a 1-inch dimension that is perpendicular to the x-axis, so I will put that in for H. That one gets cubed, and then I divide by 12. That's just part of the equation. So I end up with 8 times 1 cubed, so 8 over 12. The units end up to be inches to the fourth, and I don't know if you noticed that in these other charts, but moment of inertia was inches to the fourth. Inches to the fourth. Okay. Now that's a relatively small number. 0.67 inches to the fourth. That's not very much at all compared to, let's look at it compared to some of these other beams. Well, this is a S24. So remember, the 24 is roughly how deep the beam is, or you might say how tall the beam is from the top of the flange to the bottom of the flange. So ours is actually what? 8 inches. Let's see if we can find a S8. Oh, well, these are S values. Let's look for a T. WT. So there's a WT8 right there. So WT8, but it has moment of inertia of like 77, 42, 23, and we're at 0.67. So there's got to be more to it than what we've done. And there is more to it. So what this number is, the 0.67, that is the moment of inertia of the flange about its own centroid. So that's like taking a ruler. I probably have one. Yeah, here's one. Taking a ruler, and you know, because this would look like the flange if we had a beam. I don't have a T-shaped beam. Actually, I did have one. I don't see it now. But the flange of the beam, putting loads on it and thinking that it's gonna resist very much, but you know, it doesn't resist hardly at all. It's gonna bend really easily. Now, if I did it this way, same exact beam, but I do it this way, put the loads on it, that's actually pretty hard. I don't think I could make that bend, you know, bend down like this. And what's happening when I do that is that I'm flipping the 8 and 1 in the equation. So the 8 becomes the cubed number, and the 1 is the not cubed number. So suddenly I go from 8 times 1 cubed over 12 to 1 times 8 cubed by going from this orientation to that orientation. The 8 and 1 flip when I do that. And what's 8 cubed? 512 over 12. So I end up going from 0.67 inches to the fourth, where I'm at now, to 43 inches to the fourth, just by changing the orientation of the flange. Now, I'm not going to do that. That's just pointing out that it does matter that you get the base and the height in the right position in the equation. Now, the other thing here is that this 0.67 is the moment of inertia about the flange's centroid. But I want the moment of inertia about the T-beam centroid. And there's some distance. You know, there's some distance. We'll call that Y flange. There's some distance between the neutral axis of the T and the centroid of the flange. And so I need to take that distance into account. So what I do to do that is called the parallel axis theorem. And what this does is it's going to take the moment of inertia from one axis and translate it to a parallel axis. So that's exactly what I need it to do. I've got one axis. This is the one I just called X. Let's put XF. And XF down here, and here, same thing. So I need to translate that axis to the parallel neutral axis. The neutral axis and this one are parallel to each other. And how I do that is with this parallel axis theorem, which says that the translated moment of inertia equals the original moment of inertia, the 0.67, plus the area of the shape times what I call it, y. Well, I call it y flange, but it's y distance, I guess, squared. So the y distance is squared. In our case, this will mean I for the flange about the neutral axis equals 0.67 inches to the fourth. So that's the original moment of inertia that we just calculated, plus the area, which we could go grab from our chart up here if we didn't remember it. So it's just 8 inches squared, times y, the distance between the neutral axis and the centroid axis that I calculated this original moment of inertia about. So I've circled it there as y flange. That's actually, if you took y sub c and subtracted, well, you subtract the y sub c, or the location of the centroid of the flange, and subtracted it from the location of the centroid of the shape, the entire composite shape, the T, then that would be this thing that I've called y flange. So in our case, it's 7.5 minus 5.23, 2.27 inches. And that gets squared. So it does work out that I have inches to the fourth when I do a times y squared, plus inches to the fourth when I use the original moment of inertia. So our actual moment of inertia for the flange about the neutral axis of the T is, let's see, 2.27 squared times 8. So this number on the right hand side, this is 41.22, and this is still 0.67. So that part's not doing a whole bunch of good, is it? But when we add it to the fact that it's not at the centroid of the T, then suddenly it is having an effect. So 41 plus 0.67, 41.89 inches to the fourth. So that is just the flange's contribution to the moment of inertia of the T shape. We still have to deal with the stem. So we still have to deal with this part. So it's also a rectangle. So we can do the same exact process. The I of the stem equals the base. Now it has a much narrower base. Remember, the base is parallel to the x-axis. So this one we're doing is right here, x of the stem. So we want the 1.5 value, 1.5 inches for the base. The height of it is 7 inches. We want to cube that number. Divide by 12. So this is bh cubed over 12. Plus the area. So I'm combining the whole process in this one. So I've got the original moment of inertia here. And now I need the plus ay squared from the parallel axis theorem. So the area of this is right here, 10.5 inches squared, plus the distance between these two numbers. So we can take this and subtract them. Now it doesn't matter that it becomes negative because I square this distance anyway, so it's always going to be positive. So technically this would be a negative number, but then I square it. So 3.5 minus 5.23 is 1.73. Oops, just write it in black. Negative 1.73 inches, but then it gets squared. So now we just have some math to do. So 7 cubed times 1.5 divided by 12. 6.125 inches to the fourth plus 1.73 squared, negative 1.73 squared, times 10.5, 31.43 inches to the fourth. So plus the 6.125, 37.55 inches to the fourth. And then the moment of inertia for the T is equal to the moment of inertia of the flange plus the moment of inertia of the stem equals 41.89 inches to the fourth plus 31.43 inches to the fourth, assuming I've done those correctly. I didn't check them, but they seem all right. And that equals, oh wait, that's a 37. I wrote the wrong number there. 37. Come on. 37.55. So that number plus 41.89, 79.44 inches to the fourth. So that would be the number that we would end up with if we were trying to use the moment of inertia in any sort of equation for flexural stress or later on for beam deflection equations. So how does that compare to a T beam? So we said we had a WT8 by something. So WT8, yeah, 76, 40, 33. Now these here are much smaller. You know, they have flange widths of 10 by 1-ish. That's roughly what we have. We have 8 by 1, I think. Stem thicknesses are only half an inch, a third of an inch. You know, and we have 1.5 inch stem. So that's why ours is a good bit bigger. Okay. That's the general idea for calculating a moment of inertia of a generic shape. Now let's talk, now that we know this parallel axis theorem, let's talk about those Ix prime numbers. So where did they go? Here? All right, so here's Ix prime, bh cubed over 3. So this x prime is usually not, well, it's never in this chart, and maybe in all charts, I don't know. But in this chart, it is not at the part's centroid. So it's at the bottom of the part for all of these, at least the way they're drawn. It's always at the bottom. So what this is basically someone has already gone in and taken Ix bh cubed over 12 and applied the parallel axis theorem to that already to get bh cubed over 3. So let's take this, let's just do this and show where it comes from. So we got this. Let's put that guy over here. And based on this picture, let's just do the parallel axis theorem to move from here down to there, because that's the difference in these two. One of them is at the centroid, one of them is at the x prime axis. So it says that Ix prime would equal the original bh cubed over 12 plus the area, which would be b times h, plus the distance squared between the two, so that's h over 2. So that would just be the equation. That would be translating the moment of inertia of the centroid, about the centroid of a rectangle, to the bottom of the rectangle. That would be how we would do it using the parallel axis theorem. And so if we make this a little simpler, we have bh cubed over 12 plus we've got bh times h squared, h cubed over 2 squared would be 4. And so to, you know, combine these together, bh cubed over 12 plus this one needs to be multiplied by 3, bh cubed over 12, and I end up with 4 bh cubed over 12s, which is 4 over 12 is bh cubed over 3, 1 over 3, whatever. And that's this guy. So it completely works out fine. The thing that you have to remember is that in order to calculate the x prime numbers in this chart, where'd it go? All of these x prime numbers, they've already applied the parallel axis theorem. So you can't do it again. So you couldn't say, well, I want to use this. Well, it really shows up over here. I want to use this equation right here because it's way simpler than this equation. You can use that only if you do not apply the parallel axis theorem to the x prime equation, because it's already had the parallel axis theorem applied to it. You can't do it twice. So that's why, that's the caveat to using these x primes. You can use them as long as they're already at the location that you're interested in. You cannot apply parallel axis theorem to the x prime values. All right, because it's already been done. Can't do it twice. All right, so let's come up with an example. I'll grab one out of web work. I think I found a good one for what we want to do. Yeah, this is a good one. All right, or a good enough one. So this is about all of the things that we would need to do. It doesn't require us to write a centroid because of, well, you'll see in a minute. But other than that, it's going to have us do flexural stress, shear and bending diagram, moment of inertia calculations, all of that combined into one problem. So what we've got here is a beam, and well, I was going to say an I-beam. It's sort of an I-beam, but the cross-section is actually this thing down here. So it's made up of two channels, so the lighter gray are two channels, and then two flat plates that have been welded to the top and bottom. So it's like this really big, beefy I-beam. So that's the cross-section of this thing. Even though the beam kind of looks like a T-beam there, this is the cross-section for this beam. It has a distributed load and a point load, so there's no concentrated moment. That's fine. We have some dimensions for the plates. We have the designation for the channel, which we'll have to go find that. I don't have that chart pulled up. To create this shape, and we want to find the maximum tensile and compressive flexural stress in the beam if we have all these loads on it. So that means that the maximum one, we can't just easily look at this beam and tell where the maximum internal bending moment is. So we're going to have to draw the shear and bending diagram and figure out where and what the maximum bending moment is. Then use that in our bending stress equation, the my over I. And that equation is going to need us to calculate I, because we have partly standard beams, but they've been enhanced with these plates. So there's a lot going on in here. Again, this would not be a single test question. This is a lot of things all at once. So don't get too worried that it's going to take us the rest of the time just to solve this thing. All right. Here's what we've got. So before we can do, well, there's a couple of things you could do first. Since we just got done doing moment of inertia stuff, let's do that first since it's fresh. And then we'll go back and do the shear and bending and all that kind of thing. So here's our cross section that we're dealing with. We've got a couple of pieces of information. We've got that these channels are C254 by 45. So that's what the two channels are. So this guy and this guy. The plates for me are 240, these are in millimeters, by 30. And they're both the same, so they're identical. All right, so I don't have to worry about the centroid for this one because I can just put, I can tell that I just have to put the y-axis right in the middle and the x-axis also right in the middle. And that way, if I do that, x sub c is 0, y sub c is 0 just by symmetry. So I don't have to go and calculate anything for the location of the neutral axis or the centroid. So the centroid is right here. Notice it's not even in part of the beam. This part right here, this is hollow. So there's nothing there. So the centroid is in a part of the beam, the composite beam, that doesn't even exist. You know, it's just a hole. So that's fine. Let's work on our moments of inertia for this thing. So first, the C254 by 45, we can just look up those once we find the table that has 254 by 45 in it. So let's find that table. I'm pretty sure that it's not this one, but let's look. No, this is it is a C chart, but this one has, the largest beam is C18 because these are inches, and that other beam designation is in millimeters. So we can't use this chart. Let's look in exam reference 1, see if it's in there. I'm not sure which one it's in. Let's see. There's none of them. So let's look in exam reference 2. WC. All right, so it's this one right here. We just got to rotate and zoom. There we go. So there's our C254 by, it was 45, right? Yes, 254 by 45. So there's 254 by 45. We have, again, we have the two different options, 42.9 and 1.64. Let's check our picture, yeah, just to make sure. Our beams are oriented standing up like this, where the load, it doesn't specifically say. Oh, I lost a picture. There we go. Let's go back and check this. It doesn't, specifically say that the loads are applied up here, but there's no reason for me to think that they drew the beam cross-section sideways. So I'm going to assume that the loads are perpendicular to the XX axis in this picture. So that puts me under this column with 42.9 being the, and those units are 42.9 10 to the 6th millimeters to the 4th. So 42.9 times 10 to the 6th millimeters to the 4th for the moment of inertia of the two channel beams that comprise this thing here we've got. So let's write that down. I for the C beam is 42.9 times 10 to the 6th millimeters to the 4th. Okay. And there's two of those, so when I'm creating the entire moment of inertia for the composite beam, I'll just multiply this number times 2. They have their centroids right here and right here. They're already at the neutral axis, so no parallel axis theorem is needed. I could do the parallel axis theorem to a standard beam because I have the area of the beam listed. It's 5690 millimeters squared for this beam. So I could do A times Y squared and use even a beam that has its own designation. I could apply the parallel axis theorem to that if I needed to. I don't need to in this case. These little welded on plates at the top and bottom, they're also identical. They have the same distance from the neutral axis. One is positive, one is below it. But remember, in my parallel axis theorem, that distance gets squared, so it doesn't matter. So I just need to calculate one of them and multiply times 2. So let's do I for the, let's call them the plates. So we'll do P. So it equals BH, they're rectangles, BH cubed, so 240 millimeters times 30 millimeters BH cubed over 12. So that's the moment of inertia of the top plate about its own centroid. And the bottom plate would have the same number. Plus the area, 240 times 30. Let's see what that is. 7,200 millimeters squared times the distance from here to the neutral axis. So it's basically half of the plate plus half of the height of the C. Now, I know that the C has a nominal height of 254 millimeters, but let's check the actual height. They call it depth in the chart here. And it is. It's exactly 254. So that's an easy thing. So that means that this distance is going to be 15 millimeters plus 254 over 2 millimeters squared. Now all we have to do is do this math. 30 cubed times 240 divided by 12, 18,000. Plus this number, 254 divided by 2 plus 15 squared times 7,200, giant number, 145,180,800. So 145 million millimeters to the fourth. And I for our, let's just call it cross section, is 2 times I of the C's plus 2 times I of the plates. So the channels and the plates. And there's 2 of each. And they're identical in far as their shape, their dimensions are identical, and they are equal distances from the neutral axis for the whole thing. So remember the neutral axis is right here in this one. So I just multiply them by 2. I don't need to do them separately. So let's see. 42.9, but that's times 10 to the 6, so times 2 plus 18,000. Well, let's just put that in parentheses. 18,000 plus 145,180,800 times 2. Okay, so the whole thing apparently 376,197,600 millimeters to the fourth. So 376.2 times 10 to the 6 millimeters to the fourth, more or less. Okay, so we probably won't be able to use this number in web work because we chopped off some decimals, and web work typically doesn't like that. On an exam, that'd be fine, but web work typically doesn't like that. All right, let's work on the figuring out what the maximum bending moment is so that we can calculate the maximum flexural stress. So let's get our beam. You know what? Let's just chop it off right here. Oh, I need those dimensions. We'll cover over them. Okay. Put it at the top of the page because we're going to draw our shear and bending diagram below it. Oh, we need all our dimensions. Let's see. Let's just grab them and copy them down there, and then we'll get rid of them. All right. So 25 kilonewtons per meter for P1. L2 is 3 meters. Let me put this down here. P2 is 35 kilonewtons. L1 is 6 meters. Let's put these up here. And L2, oh wait, L1. Oh, there's 2 L2s, okay. That makes more sense. All right. Now we need our, I wonder if this, no, it just draws a box. All right. Let's cover this guy up and cover this guy up. This will be the reaction at A. This will be the reaction at D. Let's take our distributed load, 25 kilonewtons per meter, spread over 6 meters. 25 times 6 is 150 kilonewtons. And that will be at 3 meters. All right. Let's write our summation of moments about point A. A is the pin on the left-hand side. And we've got 150. I'm going to leave the units off so that they're not as, so that I can fit the equation on the screen, basically. They're all correct you know, they're all kilonewtons and meters, so we don't have any mixed stuff. 35 times 9 minus RD times 12 equals 0. Therefore, the reaction at D is a positive number, so we drew the arrow the right way. And the number is 150 times 3 plus 35 times 9. All of that divided by 12, 63.75 kilonewtons. And then we can do summation of forces in the y direction equals 0. Now, here's the thing. I mentioned it last time, but if I do this, moments and then forces in y, I can get the shear diagram to come out as starting at 0 and ending at 0, kind of making me think I did it right. And really, I just made an error somewhere, but these two equations will force it to be right, and I don't know I'm wrong until I draw the moment diagram. But if you do this one, summation of moments about D equals 0, now these two are not related to one another. You know, this moment about D does not depend on anything I did in the moment about A equation. So if I do these two, then, and I get starting and ending at 0 on my shear diagram, then I actually have a check that I've done them right. So this might be a better approach here. So let's see, 35 times 3. Now I could have still written something down in the, you know, the sketch wrong and carried that error to both of them, but we'll try not to do that. Minus 150 times 9, and then plus RA times 12 equals 0. Therefore, RA equals, let's see, 35 times 3 plus 150 times 9 divided by 12, 121.25 kilonewtons. I suppose you could do 121.25 plus 63.75. That's 185. And I have 150 plus 35 going down, so that summation of forces in y checks out, that they both equal 185. So that's another little check you could do. All right, so let's put those in. RA 121.25, RD 63.75. Now let's draw our references. Let's get it. Oh, all right, something like that. I want it kind of on the screen. Okay, and let's draw a horizontal line for where we're going to put the shear. Oh, wait, I wanted a straight one, though. Oops. No. I held down the shift key for too long. So that's V equals 0 kilonewtons. Or we could do 0 and then put our units down here. All right, we start at 0. Let's draw them in blue. Start at 0. And let's get an idea. We're going to go up 120, then drop down 150. So it's a pretty straightforward diagram here. But we need to have these equal to maybe 40 to have our scale. It doesn't really matter if you have the scale of these correct. It does help if you're too far off on the scale and one of these crosses 0, you might not, it might not look right. So spend 5 seconds trying to get the scale more or less right. All right, so we go up to 121, so we'll put 121.25 here. And then we encounter the distributed load, which is not an instant change, it's a gradual change. So I'm at 121.25. I lose a total of 150. So by the end of the distributed load, I am at negative 28. So this is negative 40. So negative 28 is like right here. 0.75. And it's a straight line between the two. And it's a negative slope because the distributed load is pointing down. So it's decreasing the amount of shear as you apply more and more of this. that might seem weird, like the amount of shear is decreasing as I apply the distributed load, but the shear was sent to its highest point because of the pin, and now it's, not decreasing the amount of shear as much as this is what caused the increase at the pin. So it's kind of backwards from the way I'm looking at it or saying it. All right. So let's draw a horizontal line here. There's no shear forces, or no forces that create shear at all between B and C. Then I go down another 35, so minus 35 gets me down to 60, or negative 63.75. So it's going to go right there. And then I go across. There's no change in shear until I get to the roller at the end, which happened to have a reaction of positive 63.75. So I'm back to 0. So there is our shear at any point. You don't have to color these things in. I just usually do for some reason. I'm not sure why. All right. Now, usually the best thing is to start calculating these areas of all of the shear diagram. Remember, the moment diagram is basically an integration of the shear diagram with the concentrated moments, the external concentrated moments interspersed in there. This one has no concentrated external moments on it. Those are these guys. We don't have any of those on here. So ours is really just going to be integrating the shear diagram. So this area is a height of negative 63.75 and a base of 3. So negative 191.25. This one, 28.75 times 3, negative 86.25. These are kilonewton meters, would be the units. The height of the shear is kilonewtons, and the base of the rectangle is meters. This one, I have to figure out what my dimensions are. So I've got to know what this and what this equal. X1 and X2, we'll say. So the way to do this is take the height of this triangle that is crossing 0, so 121.75, and divide by the slope of that hypotenuse. The slope of the hypotenuse is the magnitude of the distributed load. So the slope here is equal to negative 25 kilonewtons per meter, which is the value of the distributed load. So 121.75 divided by 25 is 4.87. And you could do the same thing for x2, 28.75 divided by 25, or you could just say 6 minus 4.87, either one. 1.13. Those are all meters. All right. Let's scroll somewhere there, and let's put our reference bending moment diagram down here, and we'll have M equals 0, and the units here are kilonewton meters, and we're going to start at 0. And a lot of times I like to go in and also remind myself well, that's not what I wanted to remind myself. Remind myself where this intersection occurs. So we'll put that in as a line also. All right. So we're going to go, let's see. Oh, I didn't do the area. Hold on. Now I can do the area of these two triangles. 121.25 times 4.87, but it's a triangle, so divide by 2. 295.24, and then this little one, 28.75 times 1.13 divided by 2, negative 16.24. All right, so we start at 0 for our bending moment diagram, and we gradually go up to 295, or go up by 295, which is 0 plus 295 is 295. So that's going to be our peak, but we'll do the whole thing. Let's make oh wait, that's got to go to 300 almost. Let's count by 30s. 30, 60, 90, 120. There we go. 300. All right, so we max out at pretty much right there. So 295.24, and this one starts out with a large shear, the 121. So it's a steep or large slope, and it's positive. All this shear in this first triangle is positive, above 0. So it means to have a generally positive slope. Generally that, but it's not a straight line, because the further right I move, the shear force gets smaller and smaller and smaller until it eventually gets 0. And the slope of the moment diagram, when the shear is 0, the slope is 0, which means it's horizontal. So I'm going to have a shape that looks something like this. It's going to be, horizontal here and pretty steep here, and something like that. And then I'm at 295.24. I subtract off 16.24. So I'm at 279. So something like that. Also curved. Then I subtract off 86.25. I'm off by 1 somewhere. I'm not sure where I lost a 1, but that's okay. I'd probably just, I don't know. Hold on, 63.75 times. No, I lost 1, or like half somewhere. So the 279 minus 86 point, I think that's 25. So that gets me to 192. So that's right in here somewhere. 192.75. This one is a straight line because the shear in this section is constant. So that means I have a constant slope. And then I've got negative 191. I've got positive 192. So I end up pretty close to 0. I want to put it at 0. This one's a constant slope because it's a constant shear. And notice these, when you're careful about drawing them, the slope here and the slope here are not the same. And the slope on 1 is more shallow than the slope on 2. And if you look at the shear, the slope in 1, the region I marked 1, is less than the shear force. I mean, it's negative, but the absolute value of it is less than in section 2. So the section 2 with the greater shear force, even though it's a bigger negative number, we're looking at an absolute value because shear doesn't care if you shear in one direction or the opposite of that direction. So then the slopes show the higher shear force. All right, what we're really interested in, I'm not going to color this one in. What we're really interested in, though, is this point, sigma max. So sigma max equals 295.24 kilonewton meters, and then that is at 4.87, or x, let's just do x equals 4.87 meters. Assuming you measure from the left end of the beam. Now you probably, that's in the sort of, not the middle, but that's in the length of this distributed load. You probably would not have been able to just look at this and say, oh, well, the maximum bending moment is at 4.87 meters from the left end. So that's why these shear and bending diagrams are useful, is because they give you a relatively quick way to go in and find the location where the maximum flexural stress is. So now we've got this. We've got max flexural stress. We've originally had, oh no, it's up here. Moment of inertia. And we have our flexural stress equation. Sigma equals negative m times y over I. Now we need our cross section back. Let's find it. It's right here. So in this case, Well, let's see what the problem's asking for first. Let's see. What is it? Because I cut that part off. Okay, it wants the flexural stress on the top of the beam and the flexural stress on the bottom of the beam. So that's easy enough. So on the top of the beam, in our equation, sigma equals negative m times y over I. This y value controls the point of interest. And it's measured from the neutral axis. So for the top of the beam, you know, maybe right here, y is going to equal 30 plus half of 254 millimeters. For this point, it's the same exact thing, but it's negative. So let's go back to our equation. M max equals negative, well, not negative, negative's in the equation, 295.24 kilonewton meters times y, which is 30 millimeters plus 254 millimeters over 2. And let's say we were doing the top of the beam. So this is the measuring from the neutral axis up to the top. And I is 300, or that number, 376,197 600 millimeters to the fourth. All right, so I've got some mixed up units in here, so we'll have to get those straightened out before we can actually do anything, but let's work on this. Let's see. So let's do the 254 divided by 2 plus 30. So this number is 157 millimeters. Let us, what should we do? Let's just convert everything to meters, and we'll leave the kilonewtons alone. Let's convert everything to meters. So this needs to be times 1,000 millimeters in 1 meter. This guy, same conversion factor, except it has to be to the fourth power to get rid of millimeters to the fourth. All right, so let's see if we can do this. My calculator may not like it. Okay, that 157 divided by 1,000 times 295.24 divided by the denominator. All right, so I get a number. Negative 123,213.65 kilonewton. Well, no, kilopascals. So if I want megapascals, negative 123.2 megapascals. Because normally you don't report things in kilopascals. It's certainly not 123,000 kilopascals. All right. And for the bottom of the beam, negative m times y over I. Everything is exactly the same except y is going to be negative 157 millimeters. So it's going to equal the same thing except it's a positive 123.2 megapascals. And so that shows us positive is tension. And that means that on the bottom of the beam we have tension. So if we look at our loading situation here, it does make sense that this beam would be bending, you know, something like this, where the bottom is getting stretched out and the top is getting compressed. And we did get those kind of numbers. Let's see if we got the right numbers. So we're supposed to have 123.2 megapascals. Let's see. Oh wait, top was negative. Bottom is that. Let's see. No. Oh, well, all right. 122.4, and we put 123.2. So somewhere we made some little error. That is not wrong. It is web work wrong because we were off by 1 here. So there's possibility that somewhere in here, it could be this 295 even. 121.25 times 4.87 divided by 2. No, that looks okay. But it is rounded. That's 295.24375. And so there's little bits of rounding scattered all in here. And I assume that little bit of rounding somewhere, probably in this internal bending moment value, has caused us to be ever so slightly off and not web work correct, but that's okay. We're gonna fix that because we can see the answer. There we go. But on the exam, that would be a perfectly fine answer. Web work just gets so picky about the things. It's what we have to work with, so that's what we'll do for now. But if you are doing all of this correct, and web work's giving you a problem, put this thing over in MathCAD so that you don't have to round things, and that will help. It's going to be tough with trying to draw the shear and bending with keeping track of every little decimal, but that kind of, we started rounding when we calculated the areas, basically. And then those areas travel on into here, although we only had to get the first one right, so we're not that far off. And we did use, you know what, we rounded some in here a little bit. No, we didn't. I don't think we did. I think all these numbers are exact. So our rounding is potentially just in that 294.24, which is supposed to be, where did it go? Let's see if we get this. Well, I don't want to plug all that back in. That's a pain to do. I think our rounding error is in this one. I don't worry about it in the real world, but in web work world, you have to worry about it. All right. I think for now, that's enough of this stuff. I've opened up homework something or another 13. This was from the optional, the one that we worked in class. It was optional 2. Yeah, homework 13 is open. Homework 12 closes soon, so don't sit on that too long. Also, today is the where are we at? Lab 1 beginning. Now, normally, like I said last time, this Lab 1 would be, we would have the goal of we're going to build this truss. We're going to laser cut some wooden pieces, and we're going to build a truss, and you're going to test it and everything. But since y'all are scattered all over everywhere, we can't really do that. So it's going to be more on the, we'll design and analyze a truss, and we will test it digitally. So Lab 1 has you building a common tensile test specimen. So let's look at the lab. You're going to build your own geometry, but there is a standard geometry size, an ASTM standard for the actual flat tensile test specimen. I'll see if I can dig that up so you can see the actual geometry. I think I have it. But I do go, here is a YouTube video. If you're not sure how to use SOLIDWORKS to do one of these simulations, you can just follow the video and put your numbers in and create your SOLIDWORKS simulation. If you don't have SOLIDWORKS, then you can request it